On this video, we're going to practice using what we know about the first and second derivative and finding relative extrema and inflection points, and then put it all together to graph a pretty complicated function. So we have y equals x squared minus 4, the quantity raised to the 2/3. So first, to do the first derivative stuff, we're going to find the first derivative. This is a chain rule derivative, so we're going to get 2/3 times, we'll leave the inside function x squared minus 4 alone for now, to the subtract 1 from the negative 2/3, or from the 2/3 rather, and it's a negative 1/3, times the derivative of the inside function, which is 2x. So we can write that as the 2 in the numerator of 2/3 is going to hit that 2x and make it a 4x in the numerator. The 3 from the 2/3 will go to the denominator and join our negative 1/3 as the cube root of x squared minus 4 in the denominator. So there's our first derivative. We're looking for critical points, so we want to find places where the derivative is 0 or undefined. So really that comes down to two questions. Where is the numerator equal to 0? And where is the denominator equal to 0? So the numerator being 0 will make the derivative equal to 0. The denominator being 0 will make it undefined, make the derivative undefined. So we're going to get 0 is one critical point, and dividing by 3 and cubing both sides, we're going to get to x squared minus 4 equals 0. So x is going to be a positive and a negative 2. So we have critical points, 3 of them, 0 and positive and negative 2. So we're going to do a number line for our first derivative. We're going to label that as f prime. We're going to put 0 in there, 2, and negative 2. Now we're looking for the sign of the derivative in each of these regions. Now when we plug in, say, a negative 3, the numerator is going to be a negative, and squaring negative 3 is going to be a positive 9 minus 4 will be positive, so that denominator is going to be positive. A negative divided by a positive is going to be negative. If we plug in something between negative 2 and 0, say negative 1, our numerator for x will remain negative. Now negative 1 squared minus 4 is a negative 3. The cube root of a negative is negative, so the denominator will be negative. A negative numerator over a negative denominator will make that be positive. Plugging in positive 1 will make the numerator positive, but the denominator will remain negative, which makes the derivative negative. And to the right of 2, then everything is going to be positive, and so we will get a positive. So to answer part A, the function will be increasing when where our derivative is positive. So that's going to be from negative 2 to 0, including the endpoints, and also from 0 to infinity, including the 0, and we can never include infinity. F is going to be decreasing where the derivative is negative. So that's going to be from negative infinity to negative 2, including the negative 2, and between 0 and 2, including both of those. So to get part C, to find relative extrema, then we can see that our derivative goes from negative to positive at negative 2. So that's going to be a relative minimum. And when we plug negative 2 back into the original function, negative 2 squared is 4 minus 4 is 0. So that's going to make negative 2, 0 be the relative minimum. I didn't ask you to justify it, but just for the record, if I did, you would say that's a relative min because f prime changes from negative to positive there. Now we also have a relative minimum at x equals positive 2, because we can again see the derivative goes from negative to positive, and that's also going to be 0. So we have relative minima at negative 2, 0 and 2, 0. our derivative goes from positive to negative at 0, that's going to make that be a relative maximum. And when we plug 0 into our original, we're going to get the cube root of negative 4 squared. Well, I'm going to do the squaring first. So negative 4 squared is 16, so it's going to be the cube root of 16. Not a real nice number, but we can figure out where to place it when the time comes. So we have now, I guess that was B. I wrote that as C. Let me change that. This is part B. We have found the relative extrema. So we've gotten all the information we can now from the first derivative. So we're going to move on to the second derivative. So we are going to find the second derivative, which is the derivative of the derivative. So I'm going to look at this right here, our derivative, and let's see if we can do our quotient rule. So we have our denominator, which I'm going to write as 3 times x squared minus 4 to the 1/3 power times the derivative of the numerator, which is 4, minus the numerator times the derivative of the denominator. So we're going to take that 1/3 times 3, so that's going to cancel. And then that's going to be x squared minus 4 to the negative 2/3 power, and then from a chain rule times the derivative of x squared minus 4, which is 2x. This is all over the denominator squared, which is going to square the 3 and be 9. And I'm going to write that as x squared minus 4 and 1/3. When we square it, we multiply the exponents. So that's going to be to the 2/3 power. Now, ultimately, we're going to try to look for potential inflection points. So ultimately, we want to set the numerator to 0 and the denominator to 0. But first, let's do some pretty serious factoring here. So when we see these powers, we have the x squared minus 4 to the 1/3 and also to the negative 2/3. Our general rule that will serve us well is we're going to factor out the smaller of the exponents. So in this case, a negative 2/3 is smaller than the 1/3. Now we're also going to, I bumped something wrong there. We're going to factor out our least common denominator between numbers. So we have, let me get my pen back up here. So we have a 3 and a 4 here, that's 12. We have a 4 and a 2 there. They have in common a 4. So I'm going to pull that out. Now let's see what we've left behind. So we took out the 4, the 3 is still there. So we have our 3. Now when we take out the negative 2/3 exponent, then that's like dividing this by x squared minus 4 to the negative 2/3. To divide by the x squared minus 4 to the negative 2/3 means we're going to subtract the negative 2/3 from the 1/3, which is going to make that be a much nicer x squared minus 4 to the first. See how that works? Minus, we took out the 4, we still have a 2, an x, and an x, so that's going to be a 2x squared, and we pulled the x squared minus 4 to the negative 2/3 out, so that's all that remains there. And we still have our 9 and the x squared minus 4 to the 2/3 in the denominator. So we're making progress. This x squared minus 4 to the negative 2/3 moves into the denominator and becomes a positive exponent, which adds to the x squared minus 4 to the positive 2/3 that's already there. So that's going to become x squared minus 4 to the 4/3. The 4 is still there, but that's not really going to make much difference. We're going to distribute and combine like terms in those brackets. That's going to be a 3x squared, a minus 12, and a minus 2x squared. So we're getting now 4 times, and I think that's going to be an x squared minus 12. and we have our 9 and x squared minus 4 to the 4/3 in the denominator. Now we're ready to look for potential inflection points, pips. So that, like we did with finding critical points from the first derivative, those are going to be values of x that make our second derivative 0 or undefined. And a fraction will be 0 when its numerator is 0, and it will be undefined when its denominator is 0. So in effect, we make this into two, hopefully, easier problems to solve. So dividing the 4 out, we're going to get x squared equals 12. X will be the positive and negative square root of 12, which, if you're okay with simplifying, is going to become 2 square root of 3. Now, on the other side, you can divide by the 9 and raise it to the 3/4 power, or if you can just see what's going to make that be 0 is x squared minus 4 equaling 0. So x squared is 4. So as we saw in the critical points, 2 and negative 2 are also pips. So our complete list of pips is going to be positive and negative 2, positive and negative 2 square root of 3, which when we go to place this might be easier to think of as plus or minus the square root of 12. That gives us a little better idea of its size. At any rate, here's going to be our second derivative sine analysis. So square root of 12 is going to be bigger than 2, which is the square root of 4. So we're going to have negative 2 and positive 2, and then we're going to have a negative square root of 12 and a positive square root of 12 here. And we're going to look at the sign of this. Let me extend that a little bit. So if we plug in something to our second derivative up here that is to the left of negative square root of 12, that might be like a negative square root of 16, which would be a negative 4. So negative 4 squared is 16 minus 2 is going to make this be positive. Let me change the sign so we can see it a little, color so we can see it a little bit better. That'll be positive. Now in the denominator, no matter what we get inside here, we're going to take its cube root, which will be the same sign, positive or negative. But then when we take it to the 4th power, this is going to be positive no matter what. So we have, in this case, a positive over a positive is going to make this part of the graph be positive. Plugging in something between negative 2 and negative square root of 12 might be something like negative square root of 9, which would be a negative 3. So that's going to make our numerator now be negative, but our denominator is always positive, so this is going to become negative. Plugging in something like, say, 0 in the middle, then this is going to remain negative in the numerator and always be positive in the denominator. And plugging in something like positive 3 in between 2 and square root of 12, now 3 squared is 9, minus 12 still is negative over positive. Finally, when we get bigger than square root of 12, this numerator is going to become positive, the denominator is always positive, and we're going to get to here. So, to answer the concavity questions, anywhere we have a positive second derivative, we're going to get a function that is concave up. So that's going to be from negative infinity to the negative square root of 12, and also from the square root of 12 to infinity. Now concave down, I think we're better off because that second derivative isn't even defined at negative 2 and positive 2. I think we should probably break this up into intervals. So we would say it's going to be concave down from negative square root of 12 to negative 2, also from negative 2 to positive 2, and also from 2 to positive square root of 12. So I think that's our part, I think that was C, and we need our inflection points. So our inflection points are going to come from where the second derivative changed sign, and that's going to be at positive and negative square root of 12. Remember our original function, we had x squared minus 4 to the 2/3. So when we plug in either a positive or a negative square root of 12, then we're going to get the square root of 12 squared is 12, minus 4 is 8, the cube root of 8 is 2, squared is 4. So our points of inflection, our inflection points, are going to be at the positive square root of 12 comma 4 and the negative square root of 12 comma 4. Okay, now I'm going to make you dizzy here scrolling because we're going to have to see what we've got here. I'm going to try to put it all together into a graph. And I think we said we had relative minima at negative 2, 0 and positive 2, 0. So those are going to be here, negative 2, 0 and positive 2, 0. Our relative maximum was, I'm going to scroll back up, it was something weird, 0, here we are, 0 cube root of 16. So 0 cube root of 16. Well, let's see, the cube root of 8 is 2, and the cube root of 27 is 3. So I'm going to say is in between 2 and 3. So I'm going to call it right in there, and that's 0 cube root of 16. That's our relative maximum. We have inflection points at square root of 12, 4, and negative square root of 12, 4. So square root of 12 is bigger than square root of 9, smaller than square root of 16, so it's in between 3 and 4. So we're going to go in between 3 and 4 and then up to 4 for the y coordinate. So I'm going to extend my axis a little bit more here and add another tick mark at 4. So we're going to be somewhere in there, which is going to be the square root of 12 comma 4. And likewise, in between negative 3 and negative 4 is going to be our negative square root of 12 comma 4 is our inflection point. Okay, now we had that it was, I believe, let me scroll back to that number line. Where was that? Here we go. There's a second. Here's our number line. So we are decreasing and then increasing, decreasing, increasing. We're concave up and then concave down all the way to the end. So decreasing, increasing, decreasing. So decreasing and concave up, then decreasing and concave down. Increasing, concave down, decreasing, concave down, increasing, concave down, increasing, concave up. And so you get something like that. Notice we had this, our function was to the 2/3 power, that x squared minus 4 to the 2/3 was our function. And we know that an even over odd is going to be a cusp. And so what we're seeing is there are actually two cusps in this graph. Both of those are cusps. All right, very good.